We will start the lecture in a minute. So let me resume. So the next set of lectures is on convolutional neural networks. So far, we've seen that MLPs are universal function approximators that model Boolean functions, classifiers, regressions. They can be trained through variations of gradient descent, where you use gradients, where the gradients can be computed via backpropagation. This is what we've seen so far. Now, in all the models that we've considered so far, the models have had a structure somewhat like what we have on the screen here. It's a multi-layer perceptron that takes in a vector of inputs and produces a single vector of outputs. But now, consider a new problem. Say you're given a speech recording, and you must determine whether the recording contains the word welcome. So can we train an MLP for this problem, a multi-layer perceptron for this problem? Assume that every recording that you get is exactly the same length. So you could be working directly on the sample values, or maybe some spectrographic representations that we convert the signal into, like we have done for homework 1. So if you get lots and lots of recordings of the word welcome and lots more recordings where the word welcome is not spoken, can you just train an MLP? How many of you think you can train an MLP just from these recordings? Anyone? So,
I mean, if we have a large enough MLP that matches the sample size, would that work?
what would the problem be with something of this kind?
We'll have
MLP has fixed size.
Pardon me?
The MLP has fixed size input.
Yes, I'm assuming that the inputs are being given, that the recordings are also fixed size. We can even assume that the word welcome is spoken exactly the same way each time. So
yeah, that's a limitation.
So even with that is not the real limitation, right? So consider, all you can do is train an MLP for the entire recording, and you might hope this would work. But then consider this. Suppose I have a recording of this kind, where the word welcome occurs in this position, and then another recording where the word welcome occurs here. Then would an MLP that has been trained to detect this word, this instance of welcome, also recognize the welcome spoken here? Would it?
No.
Why not?
Because the pattern is fixed, the MLP learns a certain pattern. So it cannot learn the other pattern until and unless it is trained for that. So you'll have to train for every instance, I guess.
So here's the real situation, right? What happens is, if I've got, let me try to draw on this one, I'm not sure if I can. So if I've got the word welcome occurring here, right? Versus the word welcome occurring here. Now, if I think of this as a bit as a vector, right? This is like having a vector where you have all kinds of stuff, and the pattern, the word that you're thinking for, occurs amongst these components of the vector. In this case, the input can be thought of as a vector again, except that the word now occurs over here. It's the same word, right? But these two are entirely different vectors. It's like comparing 0, 1, 0, 0 with 0, 0, 1, 0. They live in different subspaces. So these are two completely different patterns living in different universes. Something that recognizes this guy will not recognize this one. Something that's trained for this will simply not recognize it, even though it's the same pattern. Does that make sense? Yeah.
So I have a question here. What about the second pattern is a shifted version of the first pattern?
This is exactly the same pattern, right? Think about this. Consider this. I've given you, I've built a recognizer classifier which can detect 0, 1, 0, 0, right? Will it think this guy is also the same pattern? Will it?
No.
It should not. They're completely different spaces, right? So here the component is in the second dimension. If you call this UVWX, this is component V, this is component W. They are not going to be the same space. So now we have a problem, right? I want to compose a simple network that will fire regardless of the location of the word welcome, but will not fire if the word is not present. Or here is another problem. Here are a collection of pictures. Some of them have flowers, some of them maybe not, right? So the problem here is to train a network to determine which of these pictures have flowers in them. Now, again, if I just train an MLP that takes as an input, takes an image as an input, and produces a binary output for whether it has a flower in it or not, then would an MLP that has been trained on pictures of this kind, pardon me for stuttering, guys, it's really hot here. So would an MLP that has been trained on pictures of this kind also work on pictures of this kind? Would it? Yes, no.
No.
Why? Why not? Or why? Why?
Because the pixel level pattern is different.
It's not just that. These are completely different spaces. It is the same problem as this guy, is it not? Here the flower is here the flower is in a completely different subspace. These two images live in different subspaces. Right? That makes sense? So this first image is like having vectors of this kind, where you have where the important value is in this component, right? The second image is like having the important value in a completely different component. They live in complete different subspaces. They are not the same pattern. Make sense? Yes, no?
Makes sense.
Right. So it's not just about they're the same patterns. You have to think of it in terms of the math. You have to think of it in terms of the spaces. This may look like a picture, but eventually what you're providing to the network is a vector, right? So what I need again is a network that will fire regardless of if there's a flower in the image, regardless of where the flower is in the image. Now, in many problems like these, the location of a pattern is not important. It's only the presence of the pattern that's important. The net should fire regardless of the location of the pattern that we're searching for. Now, we just saw that conventional MLPs are not up to the job. They are sensitive to the location of the pattern. So in fact, moving the pattern by even one position is going to move this data into a completely different subspace, and the MLP will not recognize it. And you don't want such sensitivity. So you want our network, we want something that will fire regardless of the position of the pattern. So you want the network to be shift invariant, right? So if this is the characteristic we want, how would you handle the situation? Any suggestions? How could you handle it?
Take like frames and then compare the previous frame with the current frame and go on like
I already know. Okay, but what do you mean previous frame? You're getting on the way to the solution. Can somebody else suggest something else?
Scan through patches of the image.
Pardon me?
Scan through patches.
Exactly. Perfect, right? That's what we're looking for. So the easy solution is to build an MLP that detects the word welcome in a short window and scan it like so, right? And compute an output at every location. Eventually, we're going to get, we would have classified as many windows, we would have classified many windows of the input individually, and we'd have tried to detect if the word welcome has occurred in each of these windows. But then the actual question we are asking is, does this recording contain the word welcome? It's a binary question. We are not asking about, does this window contain the word welcome? So how do I translate this output to a form where I just get a single binary output for the entire recording? How can I do that? Anyone?
We can use the OR operator.
Exactly, again, right? I can just take a max. The max is really an OR. If any of these is 1, the max is going to be a 1, correct? And so if all of them are 0, then the max is going to be a 0. And even if it's a continuous valued number, this is going to give you the largest output, which is going to say that at least one frame has a probability of 0.8 of having the word welcome, which is, and if the word welcome doesn't occur, the max value is going to be 0.3 or something. So so we could do that, but you can actually improve on it. Max is only going to look at the largest value. Whereas if the word welcome does occur, then it's likely that the detector will fire on more than one adjacent window. So in fact, finding welcome in multiple adjacent windows is a stronger signal than finding it in exactly one window, because that might be just noise. So to account for this, you could combine the outputs of all the windows using a full perceptron with a softmax activation or even a complete MLP. So, but the point is that you're scanning for the pattern and then looking at and essentially computing some version of an OR on the output of the scan. So here is the pseudocode for the scanning operation. We slide through the input, and at each location we chunk out a segment of width k, where k is the width of your detector, and then pass it through the MLP, and we get one output for every position. And then we pass the collection of outputs through the softmax to get our final output that tells us that the recording has the word welcome in it. Now observe that this process is now shift invariant. Meaning we're going to find the input, find if the input has the word welcome in it, regardless of where in the recording the word has happened. But then think again, this is not scanning in combination, not just merely scanning in combination. It's actually one giant network. Each window is being analyzed by one subnet of this large network. The only difference between this large network and your traditional MLP is that all of these subnets have are identical. Basically, they have an identical set of parameters. And so this is what we will call a shared parameter network, where this is one giant network, but many subcomponents of the network have the same parameters. Moreover, this is now a shift invariant network. It will find if the input has the word welcome in it, regardless of where it has occurred. So here is again, so this entire pseudocode basically just represents one giant MLP. This is just the final output layer. In fact, I could have written this whole thing as saying y equals giant MLP of x, and that works too, except the difference is it's a shared parameter network. We can use the same solution for the flower problem too, with images as inputs. We could construct an MLP that looks at the pixel values in a smaller window of the input to detect flowers, and then sort of scan the input like so, one frame at a time, to detect a flower in each position. And at each position, this MLP is going to look at that frame and is going to output a value of which tells you whether there is a flower in that frame or not. But then this is going to give us one classification output per position, per scan location. I've arranged all of those outputs as a column over here. And if the question is there a flower in the image or not, then at least one of these outputs is going to be 1. So if I just line up all of their outputs as this one giant collection of outputs, if I just pass all of them through a max or even an NLP, this operation is basically telling you whether any of these guys or some subset of these guys found a flower, and so whether this image has a flower. But then again, the basic idea is that the entire network is basically this entire operation is obtained by scanning the input for a flower and then doing the equivalent of an OR on the outputs. So here again is the pseudocode for scanning a 2D image. We scan the input along the horizontal axis and then along the vertical axis. And at each position, at each XY position or IJ position, we sort of chunk out a segment of the input, which is the size of the window that we are analyzing, and then classify that with an MLP. And then the final output just performs maybe a softmax on the outputs at all of the locations. Again, this entire operation is in reality just one giant network with many subnets. Each window of the input is being analyzed by one subnet of this large network, and all the subnets are identical. So again, this large network is a shared parameter network where several subcomponents of the network have the same parameters. Also, this network is now shift invariant. Regardless of the position of the flower, it's going to detect whether there's a flower in it or not. So here again is this pseudocode for this entire pseudocode just represents one giant MLP. The softmax is just the final output layer. I could have written the entire operation just saying, y equals giant MLP of the image.
Professor, we have a pause.
Close to. Ten seconds, guys. So both of these are true, right? You can detect if a flower has a picture has a flower by scanning it for a flower with an MLP, obviously, which is what we've been saying. And scanning a picture for a flower to determine if the picture has a flower in it is strictly the same as analyzing the entire picture with a single large shared parameter MLP. So these are the two statements that we've actually been trying to make so far. I'm kind of dismayed that some of you claimed some of these were false. Anyway, before we continue, I'm going to introduce a change in the visualization of the scanning network because the figures will get fairly complicated otherwise. So here is, if I were trying to scan an input, this was our spectrogram. This is the equivalent of our spectrogram. So every column bar represents one vector in the spectrogram. And the scanning MLP that we've drawn so far looked like this. You had an MLP, and this MLP sort of scanned the input. And so this was the entire computation, right? At each position, it would compute and it would analyze the input, and then all of their outputs at each position were combined by the equivalent of an OR. But then when I draw it like this, it conveys some kind of a bogus idea of time. So if I draw it in this manner, then it may convey the idea that x-axis is time in every row. And so it may give you the impression that this yellow neuron is computed after this brown neuron. And that's not true. This is just one layer. This entire layer is simultaneously computed. So a more appropriate figure is this one. This figure is exactly the same as this guy, but differently drawn. I've sort of drawn these layers vertically. And so the first three neurons, the neurons in the first layer are represented in this bar. They are connected to all of the components of these vectors. The neurons of the second layer are shown in this bar. All the neurons here are connected to all the neurons here. The neurons of the third layer are shown in this bar. All neurons here are connected to all neurons here. And so, and each column is identical to every other column. Now, drawing all of the connections in this manner can become somewhat painful. So I'll use a simplified drawing of this kind, where when I draw an arrow from a bar to another bar, it means all of the components here are going to become connected to all of the neurons here. This bar means all of the neurons here connect to all of the neurons here, and so on. So is this figure making sense to you guys? I'm going to use it again and again. So just let me know if you have any doubts. Any doubts? Okay. So here is a version of the scanning network where the scan is here. When I'm scanning, the scan is proceeding 2 vectors at a time, right? So then the MLP is looking at these 2 vectors, then jumping ahead by 2 vectors, and looking at these 2 guys, then jumping ahead by 2 vectors and looking at these 2 guys. Here's a version where the scanning is moving ahead 1 step at a time. And you can see that at this position, the MLP is looking at these 2 inputs. At this position, it's looking at these 2 inputs, and so on. And all of their outputs are finally ORed. So this figure, get familiar with this. When I draw something of this kind, it means that I have this one MLP, which is scanning the input, which is why all of the bars are identically colored, and their outputs are all being passed to downstream processing. Now, getting back to our problem, these scanning ML networks are just really large networks with shared parameters. So if I want to train the network, we could just use conventional backprop to learn the parameters. So for the image problem, we provide many examples of pictures with and without flowers. The target output of the network is going to be 1 for images with flowers and 0 for images without flowers. For speech, again, I'd provide many recordings with and without the word welcome in it. The target output would be 1 for recordings with the word welcome and 0 for recordings without the welcome. And so since these are classification networks, I can use a Kullback-Leibler divergence at the output, and I can compute derivatives through back propagation and learn the parameters through gradient descent. And amazingly enough, even though I have provided the inputs which only simply have a flower somewhere in it without ever marking where the flower is, you would end up actually learning this lower level flower detector or this lower level welcome detector, and also the overall higher level structure, which can tell you if the recording has the word welcome or if the image has a flower in it. But for this to work, the constraint is that these guys are all shared. This is a shared parameter network. So these guys are all identical. All of these first level subnets are identical. So also in this case, each of these columns is identical. So, which means that when I use back propagation, if I back propagate and compute derivatives and update the parameters here, those parameters must also, that update must also reflect in all of these copies. So also if I perform backprop and update this guy, that has to reflect in all of these copies. So because they're identical, right? And this is a general issue with shared parameter networks. Scanning nets are not the only situation where you can have shared parameters. You can share parameters in any network. And the sharing changes the learning rules. To see how the learning rules change, consider the simple network, where I might just arbitrarily decide that this edge and this edge must have the same value. This weight, these 2 weights must have the same value. So Wijk and WLMN must both have the same value, which I will represent as WS, which is the common value for the set. Now for any training input, X, any small perturbation of WS will perturb both these guys, and both of these guys are going to perturb the output. and that is going to perturb the divergence. So if I look at the dependence diagram, then the common value shared by these two weights, Ws, the weight, both of the weights depend on this common value, and the divergence depends on both weights. So this is the influence diagram between the value for these weights and the divergence. So when I want to use gradient descent, I want to compute the derivative of the divergence with respect to Ws, right? And from this influence diagram, you can see that this derivative is going to be the partial of div with respect to Wij(k) times the derivative of Wij(k) with respect to Ws plus the partial of div with respect to Wlmn times the derivative of Wlmn with respect to Ws. And what are these derivatives? Can anybody tell me what are these guys? What are those derivatives?
Identity matrix.
They're the same weight. It's a scalar. These are scalars, right? It's a 1.
Okay.
And so I can just remove these two guys, and I end up with this, that the derivative of the divergence with respect to this common value Ws is the sum of the derivatives for these two weights, and those two can be computed using back propagation. So using the same logic, if we have a set S of weights that are all required to be identical in the scanning network, where I might say that I want all of these edges to be identical, then the derivative of the divergence with respect to this parameter, so all of these edges have identical weights, right? So the derivative of the divergence with respect to the common value that all of these guys have is going to be the derivative of the sum over all of these edges of the derivative of the divergence with respect to the individual edges over here, the weights at the individual edges over here. Those derivatives might all be different, right, when you just compute them. But the derivative with respect to the common value is going to be the sum of all of those guys. And so, and each of these guys can be trained using backprop. This one, which is the derivative for these terms, can be trained using backprop. And so, to train a shared parameter network whose weights can be grouped into sets that have a common value, during the gradient descent iterations, for each set of shared parameters, we compute the derivatives with respect to the common shared value Ws for the set and use that to update this Ws. And in order to compute this derivative, the derivative of the loss with respect to the shared value, we will actually perform this computation. We're going to compute the partial derivative of the divergence with respect to every element in the set and sum them all up. And these partial derivatives are computed using backprop. So the story so far, position invariant pattern classification can be performed by scanning, 1D scanning for sound, 2D scanning for images, 3D and higher dimensional scans for higher dimensional data. Scanning is equivalent to composing a large network with repeating subnets, and this large network has shared subnets. So learning in scanned networks requires a modification of the backpropagation rules, where they must be modified to combine the gradients from the parameters that share the same value. And this principle applies in general for any network with shared parameters. Any question? Questions, anyone? Was this all clear?
I have a question.
Yeah.
Could you go back to, I think, slide 64?
Okay.
Can you explain again, like the influence diagram? What is the second layer?
Okay, so there's no, this one we decided that this edge and this edge have the same value, right? So if the common value is WS, what does this mean? If I change WS a little bit, then both these weights will change, right? Yes or no?
Yeah.
And each of these weights individually affects the divergence. Yeah?
Yeah.
Okay, so that's what this influence diagram means. Okay, but when you compute perform back propagation, if you have an input of this kind, 1, 0, 0, 0, 0, 0, then clearly when you're back propagating, the local partial derivative that you compute here won't be the same as the partial derivative you compute here. Correct?
Yep.
So the derivative with respect to the shared value is the sum of these partial derivatives. Make sense?
But why we are sure they are the same? Like why WS must be?
So that's a design choice. If we decide that's the way it's going to be. Right. Consider our scan network. We know these subnets are identical, correct?
Yeah.
So I know these guys are identical.
In this case, there are several different, there are several MLPs, but in the previous one, there is only one.
This could be a design choice. I'm saying that you can always design a network with such constraints, right? This was a generic statement. And this is one instance where you see that you have all of these reds have the same value, all of these blues have the same value, all of these greens have the same value. So I'm explaining the general concept over here of shared parameters, and I'm showing how that applies to this scanning NLP.
Okay, thank you.
Right. So moving on. Yes, please turn off your mic, guys. You're supposed to be paying attention to class, not doing something else. So, when you turn on your mic, you give yourself away because it also tells me who's speaking. Right? Okay. So what we found so far is what we just saw, but then let's move on. Let's take a closer look. I'm falling behind really quickly, so I'm going to hurry up a bit, okay? Let's take a closer look at the scanning network. We have a net that scans the entire input one window at a time. And I'm going to use this speech signal as an example. And I'm going to be using this vertical bar notation representation of the network for illustration. Again, this one represents this network, right? So the lower bar represents the first layer, the second bar represents the second layer, and so on. Now, when I scan the input at the first window, each of these 4 neurons in the first layer will compute a value. And so they're going to be these, right? Which I'm representing by these 4 dots. The second layer neurons are going to compute their values from the outputs of these 4 guys. I'm representing by these 2 dots. And then the output neuron is going to compute its value from these guys shown by this dot. And then after having computed these values, which is here, the entire MLP is going to slide forward 1 step and is going to compute a new bunch of values for the next window. And then for the next window, and then for the next window, and for the next window, and so on, till it's computed 1 column of numbers for every window of the input. And then finally, all of these outputs are going to be passed through a softmax to tell you if the recording has the word welcome, right? So the complete set of circles over here represents the complete set of intermediate and final values computed by the network when scanning this input. But now let's compute the same set of values. So is this making sense to you guys? Somebody raise your hands. You have to respond quickly or we fall behind. So is this making sense? I need a yes.
Yes.
Okay, thank you. Please respond quickly, right? So now let me compute the same set of values in a different order. In the original setting, we computed the outputs of all of the layers in the network. before we slid the window forward. So the first layer analyzed this input window, then the second layer analyzed these guys, and the third layer analyzed the output of the second layer. But then consider that the first layer neurons, they just kind of get impatient. They can't be bothered to wait for the higher layers. And they sort of hurry forward and compute their values at every position in the net, leaving these guys behind. And then we go back and the second layer neurons compute their outputs from these guys, and then the final output is computed from these fellows. So in this case, is this output going to be different than in the situation we had earlier where the entire column was computed before it slid forward? Is this first output going to be different? Do you think this will be different?
No, right?
No.
Because we're now modifying.
Doesn't change the thing, right? So the output here doesn't change due to the reordered computation. So that I'm going to turn off my headset. So that's not going to change because of the reordered computation, right? So simply the fact that we redid the computation in a different order doesn't change the output of the network. But now, since we have the output of the first layer for each position, suppose the second layer neurons now hurried forward without waiting for the final output layer neurons. And then the output layer computed its values from the output of the second layer neurons. Is this guy going to be different than when we were doing it one column at a time?
No.
No.
No, right? Clearly not, because it's still the same computation. And so changing the order in which we process the input doesn't change the output. And in fact, now we can scan the output of the second layer and then compute the softmax. And the overall output is going to be exactly the same as if we had processed the entire network, the entire column, the entire network on each window before proceeding forwards. So in terms of code, here is the original scanning NLP. If we scan time, we scan across time. At each time position, we pulled out a segment of the input and passed it through an NLP. Now expanding this MLP expanding this MLP over here for the segment, what we actually did was we went over all of the layers of the MLP. And in each layer, first we computed the affine value. I'm using vector notation here. And then you computed an activation. And once this entire loop was computed, you performed and computed the final output. So this guy, you had an outer loop over time. And at each time, you had an inner loop over the layers, and then you computed an output. This is what you did when you were computing the entire network at each position before sliding the window forward. But now in this code, if I were to flip the order of these two for loops like this, would it change the final output?
No.
No, because by the time it got here, the computation is going to be the same, right? And so this is in fact what we are doing. We're just flipping the two loops, outer loops, and for computing our output, and the result is going to be the same. That's what we just saw. Now,
what advantage of doing this, Professor?
We will continue, right? That's what the rest of the class is about, right? So we can do the same thing for the 2D case, right? Now in the 2D case, you had this network. I'm calling this the input layer, but this is really just the pixels in the image. So let me make a cleaner picture. Now, so if I want to, if I have a flower detector, in order to analyze any particular window of the input, all of these guys are passing through the entire network and you're computing an output. And so when you scan the input, this network is going to compute an output for every position in the original picture. You're scanning the input and with this network, and you're going to get one output at each position. I've arranged them in the same order as the position of the window, just so that you can visually see the correspondence. And then finally, we compute a max, right? Or a softmax. But then consider what one neuron over here does. This neuron basically computes it out, when the network is analyzing this window, this neuron computes an affine function of all the pixels in the window and then applies an activation to it. So now let's say this neuron is in a hurry, right? It's not going to wait for the rest of the network, and it goes off and begins processing the entire image. So this neuron can go off and compute the entire image, and it has computed this entire map before the rest of the network works. In fact, I could do this with all of the neurons in the first layer. So the first layer of the MLP, the neurons in the first layer of the MLP hurried off and scanned the input and created their maps, where these maps represent whether this neuron has found whatever pattern it is looking for at each of the positions in the input. Then, if I want to classify a specific window, whether there's a flower over here or not, all I need to do is to pick up the outputs of these neurons when they were all analyzing this particular block and pass those guys into the rest of the network to get the output of the network for this block. So, is this making sense?
Yeah.
Right? And I can recurse this, right? But now I have these maps. So once the first layer neurons have done their job, the second layer neurons can get impatient and scan the entire input. And again, observe that in order to compute each value, this neuron is reading the corresponding value from the outputs from all of the maps produced by the first layer neurons, right? Because this neuron connects to all of these neurons. So this one is going to read the value from the corresponding position in all of these maps. And so the second layer neurons can hurry up and perform their entire computation. And then in order to decide if a particular window has an input or not, this output neuron only has to look at the corresponding locations in the maps produced by these second layer neurons. So does this make sense?
Yes.
Right? All we've done is reorder the computation. And I can recurse the logic, and now this guy can just scan these maps, and it's going to produce an output at each location. And to read the output of the MLP at any position in the input, I just have to see the corresponding location here, right? The value of the corresponding location here. So, and to detect if the image itself has a flower, I just put all of the values in this final map through an OR, which is a softmax or an MLP or a max. So this is, that could be just even a final MLP. Now, typically, there's a little you Python guys will recognize this. This is actually in the shape of a grid. To put it through an MLP, I can unwrap the grid into a vector. It's an operation we call flatten, and we can pass it through the MLP. But the point is, this is just an operation that performs some kind of an OR on the output of this neuron for every position in the input. So this is probably a more reasonable visualization of what's going on. So again, let's look at this through the lens of code. The original scanning MLP scanned through the horizontal and vertical axes. At each position, it pulled out a window of the input and passed it through an MLP. And expanding out this innermost MLP loop, what you did was you went through all of the layers, and then in each layer, so if you were in the first layer, then the first and the second layers, if you were in the first layer, then let's say your image was a picture, your image will actually have multiple maps. This could be a red, green, blue, right? So in the first layer, the neuron is going to look at a little patch. to compute an output at any position. But then the second layer neurons are just going to look at one value each, right? So if you have multiple neurons, so if you have 4 neurons in the first layer, then each of them is going to produce a map. And so the second layer neurons are just going to read one value from each of these guys to compute their output, as we saw in the figures earlier. Pardon my scribble, I'm trying to draw on a vertical screen, but I think you kind of convey the idea. So it conveys the idea. So for the first layer, sort of slicing out the input. For subsequent layers, you just operate on the output of the previous layers. You compute an affine value and apply an activation to it. But again, the key point is you're scanning the input, and at each point you're going through all of the layers. This is your standard scanning the input with a flower detector. But then if you look at this, I could reverse the order of these loops without changing the operation, and I could go through the layers in the outermost loop, and within the loops, within each layer, I could scan the input and then finally compute my output. And the output is going to be the same as before, right? So here's the final reordered code. And regardless, all we did was change the order of computation, and things remain the same. So position invariant pattern classification can be performed by scanning the input for a target pattern. Scanning is equivalent to composing a large network with shared subnets. The operations in scanning the input with a full network can equivalently be reordered as scanning the input with individual neurons in the first layer to produce scan maps of the input, and then jointly scanning the map of outputs of all the neurons in previous layers by neurons in subsequent layers, right? This is basically what we saw over here, right? So, questions?
Sorry. Another poll.
Yeah.
Is there any incentives to switch the ordering, or?
You just hang on with me for a bit, right? We still have the rest of the lecture to go through, but we have a poll. Ten seconds, guys. Hurry up, please.
So, Professor, the network that we're designing right now, that will still look for a very specific pattern, right?
It's going to be a flower detector or a welcome detector, right? Does the recording happen?
But that too when it is said in a particular way, right? The welcome.
So you can think of it this way. If you can have many different variations of welcome, and you can still have a welcome detector. That's your standard MLP problem, right?
Right.
Here we are speaking of shift invariance.
Okay.
Right? It's position invariance. So both of these statements were true. And well, some of you did get rated as false. I'm assuming you're just hurrying up to answer the poll. Now, to answer your questions, right, I'm going to try to improve on the basic scanning model. And in the basic scanning model, basically we had a base MLP. We just scan the input for target patterns like this flower, right? At each location that is scanned, the entire MLP looks for a flower-like patterns. What this means is that the first layer neurons look at this entire window of pixels that is being analyzed. And each of these neurons learns to detect window-sized features, complex patterns that span the entire window, like maybe a complete outline of the flower. And what they are doing is, in this process, they are ignoring repeatability of substructures within the window itself. And then subsequent neurons only read one value from the maps produced by these guys, right? So if this neuron wants to compute this value here, It's going to read one value from the map by the first neuron, one in the map by the second, one in the map by the third, and one value in the map by the fourth. And so the onus of detecting flower-sized features is entirely transferred to this first layer neurons. But then the fact is, if you're trying to detect flowers, flowers are composed of substructures like petals and sepals, which are smaller than the full flower, but repeat within it. And this characteristic is ignored by this setup. Now we can exploit this repeatability, but to do this, we will have to distribute the pattern detection within this box over multiple layers of the network. And here's how we will do it. Let's see how we can distribute it over 2 layers. So now the first level neurons are going to look at a smaller block of pixels, like say the size of this little white square. And they're going to scan the input to produce their maps. Now, the second layer neuron is actually going to sort of looking at a single value from these maps, because it's actually going to look, the second layer neurons are going to look at a grid of values. The grid is identical in all 4 cases. And so this second layer, so over here, the second layer neuron is computing its output from these numbers for 36 values. But then if you look at what it's actually doing, each of these yellow dots represents one of these white boxes, right? So when the second layer neuron computes its value from this grid of 9 values here, it's actually computing its output from this larger window. So the first layer neuron was looking at smaller windows, but the second layer neuron, by looking at this grid, is computing its value for the larger frame of the output. And so now we have, so the outputs of the second layer neurons at the first position are actually evaluating this entire window. And so what we've done is sort of distributed this larger window over 2 layers. Now the neurons in the first layer learn to detect smaller size patterns like say petals or sepals. And the second layer neurons learn to recognize the arrangement of these sub-patterns within the outputs of the first layer neurons. So this second layer neuron, for instance, may be able to detect that if the first neuron over here fires in these 2 positions, by fires it means it gets a high output, and that the second neuron gets a high output here, and the third neuron gets a high output in the middle, and the fourth layer neuron gets a high output here, then it's got captured some important feature with the shape shown by the white square. So these are the kinds of patterns it can still learn by while accounting for the fact that these patterns are repeatable. So you've distributed the detection over multiple layers. And again, now the second layer neuron can scan these maps produced by the first layer neurons to produce a complete maps of outputs. And at each position, they are actually effectively analyzing this larger window of the input in a location that corresponds to the position in the map itself. So for example, this output here corresponds to a window placed in the top left corner. This bottom right output, these 2 guys, would correspond to a larger window placed in this one is for the top left, and these guys would represent larger windows in the bottom right corner. And so by the time we get to the second layer, we are already analyzing the full window. And now, if you want to say, detect if there's a flower over here, then the final layer only has to look at these values from the maps produced by the second layer neurons. So over here, nothing really changed. And now the output neuron can compute an output for every position as before, get a map, and you can pass it through a softmax to determine if the image has a flower. And so now we are distributing the flower patterns across the net, the flower pattern across 2 layers of the network rather than just putting it all in, having the burden of detecting flower level features placed entirely on these first layer neurons. So is this making sense to you guys? Yes, no?
One question I have is, why does each neuron produce its own map? Like usually the whole network will produce one map.
No,
right?
so no, again, look, this map is, remember, we're going right back, you're going back several slides. This is slide 181, right? We are doing exactly the same as what we had over here. Did you understand this bit? Where I said that I could, did you understand this bit? Yes or no?
I think I don't understand why each neuron produce one map.
Each neuron is producing one value at each position. Okay. So if you go back here, if I'm computing, classifying this entire input with this network, then this entire network is producing an output at each position. And this is the map of network outputs. Do you understand this figure?
Yeah.
Okay. But to compute this output, each neuron must also have analyzed the image at every position, correct?
Yeah.
Right. So all I'm saying is these first level layer neurons, they can go ahead and do their job of analyzing the entire input without waiting for the second layer neurons. So now the second layer neuron can just read these 4 values to detect a flower out here.
Oh, okay.
Right? And I can recurse the whole logic, right?
Yeah, I think I understand now. Thank you.
Right? So that's all we are saying is we're doing the same thing now, except that we are, the first level neurons are now looking at smaller windows. And because their outputs can be arranged in the form of a map, the second layer neurons can actually look at grids, which correspond to larger windows in the output. Did this make sense?
Yeah.
Okay. But the point is that in spite of the fact that I've shared distributed the network over 2 layers, the overall operation is still just scanning the input with a shared parameter network. All that happened now was that these individual subnets themselves have further sharing of parameters. So we'll have to make minor modifications. So the structure in suppose I was scanning the input with something of this kind. So I have 3 neurons in the first layer, 3 basic neurons in the first layer, 2 in the second, 1 in the third. The actual computation when I distribute the pattern over multiple layers is going to be different. For example, this black neuron, in order to analyze this black box, this black neuron would have analyzed each of these 9 squares and produced 9 outputs. This red neuron would also have produced 9 outputs. This blue neuron would also have produced 9 outputs. And now the second layer neuron is going to be looking at, if the second layer neuron has to scan this entire box, it has to consider all 9 outputs by the first neuron, all 9 outputs by the second neuron, and all 9 outputs by the third neuron. So although this figure looks like it's connected to 3 neurons, In reality, the second layer neuron is connected to now 27 inputs. The rest of the network is the same. But once you figure that this is what is happening, then you can see that beyond that, it's still exactly just one giant network. So this is the network analyzing each block. Is this making sense to you guys?
Yeah.
Yes.
Right? It's nothing complicated, right? And so so this logic can now be recursed. I can distribute the pattern over more layers. The first layer neurons, for example, can scan the input with even smaller squares over smaller windows. The second layer neurons can look at small windows in the first layer neurons, first layer maps. Again, remember they would be simultaneously be looking at that window in all the maps produced by the first layer neurons. So each of these guys is now actually looking at a box of this size. And so when you produce this map, I'm scanning the input with a box of this size effectively. And then the third layer neuron could be looking at a grid in the output of the second layer neurons. So what has happened now is that this output now is actually looking at this larger window, but that window has sort of been smeared over 2 layers because this guy was, the size of 4, and these guys were all looking at these smaller blocks. And so this one over here, in fact, recognize so if you look at this one is looking at this block over here of the first layer outputs of the second layer neurons, which in turn represents this portion because each dot came from a little square, right? So these 4 dots together come from this region of the first layer maps, which altogether represent this larger window in the input. So again, what we've done here is we're still looking for flower-sized patterns, but then we've sort of distributed the responsibility of looking for features across 3 layers of the network. When you didn't do that, then the first layer neurons had the entire burden of detecting flower-sized features. Now they can look for smaller features, and then the next guys can look for compound features, and the next one can look at features which have compounded further still. And so and now of course this output neuron can scan these maps to produce its own map, and these guys can go through a softmax to tell you if the image has a flower or not. So now we have a distributed model where we get a flower detector at the output, but intermediate layers look at smaller and intermediate layers look at smaller and smaller regions of the input, which are hierarchically put together to get a complete full flower detector out here. So does this make sense?
Yes.
Right. So, with the more distributed representation, the scanning network it's still just a shared parameter network, except this scanning network has parameter sharing occurring at multiple layers. But the fact remains that regardless of the fact that you've distributed the feature extraction over many layers of the network, it's still scanning this image with an MLP. It's just that the parameter sharing in the MLP got more and more complicated, right? So let's see this through code again. This is for the image problem with a 2D scan without distribution. We will be scanning the image with a K cross K square window. The original scanning process was this following pseudocode. We scan left to right, then top to bottom. At each position, we slice out a K cross K segment of the image. and then pass it through the MLP. Now, if we use a simple scanning MLP without reordering the loops and without distributing the feature extraction across layers, then the MLP performs this computation. At each XY position, we go through the layers. For the first layer, we extract a K cross K window of the input and compute an affine value from it. Here, I'm assuming that Y0 is the input. And this could actually consist of more than just one image. It could have a collection of images like the R, G, and B components of an image. So C here would be 3. The segment is a K cross K window taken from the XY position of the entire set of color maps. For the higher layers, we only read individual elements from the maps of the previous layers at exactly the current position. And we compute the affine value from these selected inputs. And once we compute the affine value, we pass it through an activation to get the output of the neuron. When we reorder the computation, we flip these indices. At the highest level, we loop over the layers, and within each layer, we scan the input with all the neurons in the layer. Now, when we distribute the model, the code only changes minimally. Now, instead of extracting a K cross K window from the maps of the previous layer for only the first layer, we will now extract square windows from the maps of the previous layer at every layer. So the segment that we draw now, whereas in the previous case, only for the first layer where we're extracting a square window, and for subsequent layers, we were just pulling out one element from each of the maps. Here, for every layer, we're going to pull out a small square window of inputs from the maps produced by all of the neurons in the previous layer. Now I'm assuming this window is square. It doesn't have to be square, but square windows are symmetric and are the most popular windows. So this operation where we compute an affine value of the window of inputs and then scan the input in this operation is what is called a convolution. We will go over the exact operations of the convolution in future classes. And a network that performs its computations through a series of convolutions of this kind is called a convolutional neural network. So what we've been talking about so far is a convolutional neural network, or CNN. Now, we can also write the same pseudocode in vector notation. The weights will now be a 4D tensor, the dimensions being the number of neurons in the current layer, the number of neurons in the previous layer, and the size of the window. KL cross KL. KL is the dimension of the window in the Lth layer. So here's how we operate. We go through the layers. For each layer, we scan all of the previous maps. At each point, we pull out an image segment and compute an inner product between the weights tensor and the image segment, and then finally apply an activation. Now, why do we need to distribute the model hierarchically? What are the benefits? First, distribution forces the model to learn localized features and build up the patterns, which gives you more generalizable models. Second, this enables computations from lower layers to be reused by higher layers at different positions. And then third, and this is equally important, this greatly reduces the number of parameters in the model. So let's try to understand all of these. Let's consider this first factor. For this, let's quickly recap what we've already seen about how MLPs model their functions. They model them hierarchically. So for the most effective representation, the lowest layer neurons model some basic patterns, and higher level neurons build more complex patterns from them. And this double polygon case, for instance, the lowest level neurons learned these boundaries. And then the next level neurons built up these individual polygons, and then the highest level neuron combined them into this double polygon figure. Or in this problem, here we are given inputs that are pixel grids like this one, like you see in the old LED digital watches. The net must classify if the pattern that you see in the grid is a digit or not. Here, for the most effective representation, intuitively, the lowest level neurons would detect the basic patterns that form the digits, like these little horizontal and vertical bars. And the higher level neurons would build digit patterns from them, and the highest level neuron would pole over these. Now, this kind of representation is efficient because the lower level patterns can now be reused. For instance, this little horizontal bar over here can be used to compose 2, 3, 5, 6, 7, 9, and 0. So detecting this little bar simplifies modeling all of these digits. And so ideally, we want our model to have this kind of hierarchical representation. And we want to construct the model architecture to encourage learning such hierarchical representations. And the distributed model forces the model to learn such hierarchical representations. Now, let's consider these two factors: fewer computations and more efficient usage of parameters. And I'm going to use both 1D and 2D to explain this. First, consider the scanning model for a one-dimensional scan, like in our speech example. Now, first consider scanning with a non-distributed model, where the network is scanning over a window that is 8 time steps wide. So at each position, this is the computation performed. The first layer of neurons operates over 8 inputs. The second layer of neurons gets inputs from all the neurons in the first layer, and the third layer gets inputs from all the neurons in the second layer, and the output of the third layer go to the final softmax. If we are scanning with a stride of 2 time steps, meaning the network advances 2 inputs at a time while scanning, then this is the entire computation performed. So you'd first use the network to compute the output over these 8 inputs, then you'd advance forward by 2 time steps, and then you'd use the network to compute the output over the next 8 inputs, then advance by 2 time steps, and then compute the output over the next 8 inputs, and so on. So you're going to evaluate blocks of 8 inputs several times. And the complete computation performed is shown by this figure. Each column represents the analysis of one window of 8 inputs. And each column, of course, represents a complete network, and every column is identical to every other column. Now, I'm going to use the simpler figure to show the net, where I simply show boxes for the individual layers without explicitly showing the neurons in the layer to simplify the figure. So this again is the complete scanning network. Every column operates independently of every other column. The computations performed in one column do not in any way contribute to the computations performed in any other column. So during scanning at each position, we must perform a complete set of computations from bottom to top. Now, consider the size of the net. Let the network have 3 layers, and let the 3 layers have N1, N2, and N3 neurons. Now it's scanning the input over a window of 8 vectors in our example. So this L is the width over which of input it's considering. L is 8 here. And each of these inputs is actually going to be a vector for us. So let's say this vector has d dimensions. So these n neurons, n1 neurons, each of them require 8d weights to connect to all of these inputs. So the first layer requires a total of 8d n1 neuron weights. The n2 neurons in the second layer connect to the n1 neurons in the first layer. So the number of weights between the first and the second layer is going to be n1 times n2. And in the same manner, the number of weights connecting the second layer to the third layer is going to be n2 times n3. So the total number of parameters that we use to scan the input, regardless of how much you're striding by, what is the spacing between adjacent windows. The total number of parameters is going to be 8dn1 plus n1 n2 plus n1 n2 n3 plus whatever else is required for this topmost softmax. More generally, if this window is L vectors wide, then the total number of parameters is going to be LDN1 plus N1 N2 plus N2 N3. Now, let's distribute the model over 2 layers. So for our example, let's have the first layer neurons scan the input with 2 frames, 2 vectors, and have them stride forward by a step size of 2. So they analyze a window of 2, then hop forward by 2 vectors, analyze the next 2 vectors, then hop forward by 2 vectors, and so on. So the overall network is still analyzing 8 inputs at a time. But at the first layer, the actual computation is done by 4 identical sets of neurons. So the weights with which these neurons connect to these inputs are going to be the same as the weights with which these neurons connect to these inputs, and these neurons connect to these inputs, and how these neurons connect to these inputs. So now let's count the parameters. Say there are n1 neurons in the first block, n2 in the second, and n3 in the third. The first layer neurons read 2 input vectors in our example, and the second layer neurons read a window of 4 first layer outputs. Recall again that these 4 columns are neurons with identical sets of parameters. So we are scanning the input with this yellow bar of neurons. Now, the highlighted arrows over here show all the unique weights, all the unique parameters in the network. Since these lower level blocks are all clones of one another, the lower level block now only requires 2D N1 unique weights. Those weights are going to be the same for this one, for each of these 4 blocks. Now, for the second layer, these N2 neurons connect to each of these 4 yellow neurons, these 4 first layer blocks, but these weights will all be different. And so the second layer is going to need 4N1 because there are 4 of these and there are N1 neurons in each block. So the second layer neurons are going to need 4N1 times N2 weights. So the second layer neurons use 4N1 N2 weights. And the third layer has N3 neurons connecting to N2 neurons, so it needs N2, N3 weights. And so the if more generally, if instead of scanning having a window of size 2, the first layer neurons had a window of size k0, then the total number of parameters is going to be k0dn1 plus, again, if the second layer looks at k1 of these blocks, k1 n1 n2 plus n2 n3. Now, if I compare this network to a non-distributed network with the same number of neurons, then the non-distributed network would require 4 N1 neurons in the first layer, because there are 4 N1 neurons here. And it would have N2 neurons in the second and N3 neurons in the third. So with the full distributed scan, the total number of parameters was 2D N1 plus 4 N1 N2 plus N2 N3. Here it's going to be 4 N1 times 8D. So this is 32D N1 plus 4 N1 N2 plus N2 N3. So if you compare these two, you can see that in the first layer neurons, there has been a factor of 8 increase. Or is it 8? Yeah, actually 16 increase in the number of parameters required at the first layer if you do not distribute the model over multiple layers. So that is so distributing the model gives you far fewer parameters in this case than the non-distributed network with the identical number of neurons. Now let's consider the computations. When we scan the input with the distributed model, here's what we do. At each position, the network computes its output and then moves forward to the next position to compute its output. And so this is the next set of computations. And then to the next position, and the next, and the next, and the next, and the next, and so on, all the way to the end of the input. So this figure shows all of the computations performed by the distributed network. But now consider the first two positions. These three circled columns were needed both in the first window here and the second window here, because in the first window, the second layer connected to these 4 blocks, and the second window, the second layer connected to these 4 blocks. So these 3 central ones were common. Now, there's no need to compute these guys twice. You can compute them once and reuse them. You can use, so if you go over the entire figure, you'll see that by reusing computation of this kind, where you compute something once and then use it for multiple windows, you get a great deal of savings in computation. Now, let's extend that and distribute the model over 3 layers and scan the input. So here, the first layer is looking at 2 inputs at a time. The second layer is also looking at 2 first layer outputs at a time. So it's actually looking, the second layer is actually looking effectively at a total of 4 inputs. The third layer is now looking at 2 second layer outputs at a time. So this third layer is eventually effectively looking at 8 inputs. Again, if I highlight all the unique parameters, the 4 first layer bars are all clones, and the 2 pink bars are also clones. So only these highlighted weights are unique. Now, how many weights do we have in all? Again, assume that this input is d-dimensional. So for the first layer, we have 2 D and 1 weights. And these weights will be the same for each of these 4 blocks. For the second layer, you're going to have 2 N1 times N2, because N2 neurons connect to each of these 2 blocks, which have N1 neurons. So 2 N1 times N2 weights. And those weights are going to be the same for this pink block as well as this pink block. So you have 2 N1 N2 weights for the second layer. And the third layer, again, connects to 2 of the blocks in the second layer. So the third layer is going to have 2 N2 N3 weights. There are N2 neurons in each block. There are 2 of these blocks. So there are a total of 2 N2 neurons here. And these neurons connect to all of them. So you have 2 N2 times N3 weights in the third layer. Now, the non-distributed model with the same number of neurons would have 4 N1 neurons in the first layer, because you have 4 of these blocks, 2 N2 neurons in the second layer, and N3 neurons in the third layer. So the total number of parameters is going to be 4N1 times 8D, which is 32N1, plus 2N2 times 4N1, which is 8N1N2, plus 2N2 times N3. So which is 2N2, N3. So if you compare this one, if you compare the number of parameters for the undistributed network with the number of parameters for the distributed network, you can see that this 2D-N1 became 32D-N1 for the first layer. 2N1N2 became 8N1N2 for the second layer. So clearly, this has far, far fewer parameters than this guy. And again, when we scan the entire input with this 3-layer distributed network, here is the complete computation we perform. And again, we see that a lot of the computation gets reused. Now, even at the second level, the figure shows the computations performed for computing the output at the first position. All of these bright colors are computed for the first position. And these values are also getting reused for the third position in this example. You can see that you're reusing these 3 computations for the third position. And the reused computation comes from both the first and the second layers. Here's another example of distributed scanning, where the third layer neuron now considers 3 second layer outputs. How many parameters would we have here? The first 2 layers are the same as before. So they need 2D-N1 weights for the first layer, 2N1N2 weights for the second layer. But for the third layer, you're going to have 3N2 times N3 weights. So now again, if you try to compute the number of parameters for the corresponding undistributed network, you would find that the number of parameters in the undistributed network is going to be much larger than this, and I leave that to you as an exercise. So here is the complete set of computations performed using this model. And again, keep in mind that this entire scanning is just one giant shared parameter network. And of course, you're going to get a lot of computational benefit from reused computation. I'll let you figure out which computations are being reused and how much of a benefit we are getting. So we've seen how distributing the model over many layers gives you a large improvement in the case of one-dimensional scanning. The same clearly would also hold for 2D scans. So let's consider 2D scanning. Consider this flower picture over here. Our first layer neurons look at these little white boxes, white blocks. And your second layer neurons look at windows in the first layer maps. If this happens, then you find that adjacent windows in the second adjacent windows, when you scan the first layer maps, will actually overlap by about 75%. They overlap over these 12 values, these 12 white boxes. So the first layer response from these 12 boxes need to be computed only once, even though they are being used by multiple adjacent windows. Here, in fact, this box over here would need to be evaluated only once, but then it's going to, as you scan forward, it's going to be used by 4 windows. This box here, it has to be evaluated only once, meaning the corresponding value here has to be evaluated only once. And that value is going to be used by 16 windows when the second layer neurons scan these maps. So this happens at every layer. The more layers we distribute the computation over, the more we save from reusing computation. Now let's look at the number of parameters. Consider an image scanned using a k cross k window with an undistributed network. So then we're going to need k squared times n1 weights for the first layer. Then for the weights for the second layer, you need n1 times n2. And then for the third layer, you need n2 times n3 weights for the third layer. And of course, you need the biases. So these ones over here account for the biases. Now, if we distribute it so that the first layer neurons work on the smaller cell of K0 cross K0, and then the second layer neurons work on a K1 cross K1 window of the maps produced by the first layer neurons. Then because there are N1 neurons in the first layer, and each of these neurons is going to have K0 times K0 weights for this block. So the first layer neurons are going to require a total of N1 times K0 squared weights plus biases. The second layer has N2 neurons. Each of these neurons is looking at each of the maps produced by the first layer neurons. So these N2 neurons will look at each of N1 maps. Within each map, it's going to look at a K1 cross K1 window. And so the total number of weights used by a single second layer neuron is going to be N1 times K1 squared. And there are N2 of these neurons. So the second layer is going to require K1 squared N1, N2 weights plus biases. Now, there's no further distribution. So subsequent layers, if the ith layer has Ni neurons, then the number of weights between the ith and the I-1 layer is going to be Ni-1 times Ni. Now, when we distribute over 3 layers, we need N1 times K0 squared weights for the first layer, N2 times N1 times K1 squared weights for the second layer, N3 times N2 times K2 squared weights for the third layer, and so on. Now, these formulae may not be very enlightening. So it's useful to actually look at and put in some values to see how this gives you huge benefits in terms of number of parameters over a non-distributed network. So consider this example. Here, we are trying to scan an image using a 16 cross 16 window effectively. Now, without distribution, you're going to need 16 squared times 4. So this is a 4 to 1 net. So you're going to need 16 squared times 4 plus 4 times 2, which is 8 plus 2 times 1. So if you compute the total number of weights, you're going to get 1034 weights. If I distribute the same analysis over 2 layers with the same number of effective neurons, but where the first layer looks at a 4 cross 4 window, and the second layer looks at a 4 cross 4 window and the maps produced by the first layer, then the actual number of parameters when you work it out is only 194, which is a factor of 5 less than the undistributed model. And as the networks get larger and the patterns are distributed over more layers, this difference can become enormous. It can in fact become many orders of magnitude. And so to summarize, why distribute? It forces localized patterns to be learned by lower layers, resulting in better representations. It requires far fewer parameters, and you also get an enormous amount of savings in terms of reused computation. But the key intuition to retain through all of this is this: regardless of the distribution, we can use the convolutional neural network as scanning the input with an NLP. When the model uses distributed representations, we just have more parameters, more sharing of parameters in the network. And so the story so far: position invariant pattern classification can be performed by scanning the input for a target pattern. The operations in scanning the input with a full network can be equivalently reordered as scanning the input with individual neurons in the first layer to produce scanned maps of the input, and jointly scanning the maps output by all the neurons in previous layers by subsequent layers. The scanning block can be distributed over multiple layers of the network, and this results in significant reduction in the total number of parameters. And so we've gone through most of the topics for this lecture, but we have some final touches to wrap up this lecture. First, let's introduce some terminology and then discuss how we can scale the representations and how we can account for minor jitter in the patterns. Again, here is how the hierarchical model works. Each neuron, we're going to see this slightly differently than before. Each neuron can be viewed as scanning the input and redrawing the input, except it's not re-imaging the input. It's drawing an image of where at each position in the input it's scoring the presence of specific patterns, specifically the features that the neuron is trying to detect. So the first layer neurons scan the input with a small window, say the size of a petal. So each neuron scans the input for patterns of the size of this window. And these maps painted by these neurons mark whether these patterns are detected at each location in the input. Each of these neurons will detect a different pattern. For example, one of them might find oriented petals, the second might find stamens, the third might find a sepal, and so on. The second level neurons look at small windows in the maps output by the first layer neurons, but are effectively looking at a larger region of the input. So these neurons put together the patterns detected by the first layer neurons. For example, they may put together multiple petals and sepals into a larger part of a flower shape. And so by putting these component patterns detected by the lower layer neurons, they create larger patterns that they search for. And so the second layer neurons scan the input and produce maps of where in the input these larger patterns may be found. Still higher neurons look at windows in the maps produced by the second layer neurons and compose patterns. Basically, they create a composition of the patterns detected by these first layer neurons into still larger patterns of the input. And then they scan the input for these larger patterns and they produce their maps. We can have any number of layers of this kind. Each of these scanning neurons is usually called a filter. Detecting patterns is like having a filter that only lets the target pattern through. So each filter scans its input maps, looking for its own target patterns. The pattern in the input image that each neuron responds to is its receptive field. The squares in the figure show the receptive fields for the first, second, and third layer neurons. The actual receptive field for the first layer neurons are simply their arrangement of weights. The weights are arranged in exactly the same shape as the window because you have one weight per input pixel. So if you visualize the weights, that would be the pattern that the neuron is trying to find. That is its receptive field. For the higher level filters, the actual receptive field is not immediately obvious and must be calculated. What pattern in the input, what patterns in the input do these filters actually respond to? I've been saying that there will be petals, parts of flowers, sepals, and using flower component terms. But the reality is we can't really say what patterns these neurons will be looking for. They won't be simple and they won't be as easily identifiable as petals and inflorescence, because how a model composes the patterns that we ask it to detect cannot really be predicted. Typically, the maps produced by the last scanning layer are not arranged as rectangular maps, but as vectors that are passed to a softmax or an MLP. So the rearrangement of these maps into a vector is often called flattening. With the terminology behind us, let's look at typical modifications in the basic structure. The first is the stride of the scanning. The stride is how many positions the window shifts at each step of scanning. If the stride is 1, then for example, if the stride is 1, then the neuron produces 1 output for each pixel of the input. So the output map will be approximately the same size as the input, except for some edge effects. If the stride is greater than 1, say if it is 2, then the neuron produces 1 output for every alternate pixel of the input. So the output maps shrink by a factor of 2 in each direction. Having a stride greater than 1 may seem to lose some information, but from an algebraic perspective, it doesn't. If the total number of elements in the output maps across all of the neurons is at least equal to the total number of elements in the input maps, then in principle, we could retain all the information about the input, even though the maps have shrunk in size. The only requirement is that in the process of striding, the filters must not skip any components of the input. So if we have, but then for this to hold, the number of maps has to increase. So if we have a stride of 2 while scanning, then the number of output maps must be 4 times as many as the number of input maps if we don't want to lose information. Shrinking the maps allows the net to search for more patterns without increasing the overall number of elements in the map too much. So here is the updated pseudocode for convolutional neural networks with strides. Each layer of the network, as you can see here, you can scan along X and you can scan along Y. But then when you advance along each of these dimensions, at each time you advance by stride indices. So M and N over here are the indices over the output maps, which must be incremented once per stride. Another key modification that is used to account that in convolutional networks is used to account for jitter in subpatterns. Now consider we are putting together petals and other low-level patterns to compose a flower. If one of the petals shifts just by a pixel, does this completely change it from being a flower, or is it still a flower? Clearly, just this minor jitter doesn't change the overall pattern. It remains a flower. So we want to modify our model to permit such jitter. We will do this by changing our activations. For this, we will introduce what are called pooling neurons. Your standard neuron computes a function, an output of this kind. It applies an activation to an affine function of its inputs. And so you'd first compute this affine function, then apply an activation like a ReLU or a sigmoid. Pooling neurons, on the other hand, compute a jitter or permutation invariant function of their inputs, which is typically some kind of a statistic of the inputs. That way, if the peak values in their patterns, input patterns, or in their receptive fields jitter a bit, the output will not change, giving you jitter invariance. So here are some typical pooling activations. Max pooling simply outputs the largest of its inputs. Mean pooling outputs the mean of its inputs. Both of these don't change if you reorder the inputs. So these are jitter invariant. Now, you can have other such jitter invariant activations. Now, pooling activations only make sense after a layer of regular neurons with the usual kind of activations of this kind. So the regular layer detects the patterns in the input, and the pooling layer, layers of pooling neurons, introduces jitter invariance over it. Pooling layers are typically used with a stride greater than 1. So they result in a shrinking or downsampling of the input maps. So their output maps are smaller than their inputs. And so this overall structure, composed of layers of neurons which scan their input maps for patterns, followed by a final flattening and an NLP, is called a convolutional neural network. Here is the famous convolutional neural network that really brought CNNs into the limelight. This was implemented by Jan LeCun in the late 1980s. The problem was that of recognizing handwritten digits. This used to be a big problem for the US Postal Service. So LeCun built the CNN that had such good accuracy that I believe the USPS used it for a long time. The network operated on 32 cross 32 images of digits and had two convolutional layers, each followed by 2 regular convolutional layers, each followed by pooling layers. The first convolutional layer had 4 filters. The second one had how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 filters. And we'll see this architecture in a little more detail in a couple of lectures from now. Now, we've been looking at the distributed model applied to 2D images with 2D scanning. We call that a convolutional neural network. When we apply to data like a spectrogram, speech spectrogram, then the scanning is only in one direction. And then we call it a 1D CNN or a time delay neural network. For speech, the input would be the speech spectrogram, which is a 2-dimensional representation of the signal. The x-axis is time, and the y-axis represents frequency. We will only scan along time. And the pattern we are looking for may be quite wide, as shown. The neurons in the first layer scan the input with much shorter windows. So each neuron would produce a series of outputs by scanning. And so the entire first layer together will create a collection of such sequences, which form a matrix of about the same length as the input. We can also decrease the length of the outputs by using a stride greater than 1. The second layer will have a receptive field, which is wider than the receptive field of the first layer. So to achieve this, each neuron, second layer neuron, scans the output matrix of the first layer neurons with a window that's several columns wide. And so each second layer neuron outputs a scan, and these form a matrix that is also the same length as the input. The third layer neurons are required to have a receptive field that is even wider than that of the second layer neurons. And so they scan the output of the second layer neurons with a window that is also several columns wide to give you a wider receptive field over the input. And the scans of the final layer are subsequently sent to a softmax. This entire structure with the 1D scan is the well-known time delay neural network. In fact, this model was invented right here in CMU by Kevin Lang in the late 80s and came even before Jan LeCun's CNN. And so here's the story so far. Neural networks learn patterns in a hierarchical manner, simple to complex. Pattern classification tasks such as, does this picture contain a cat, are best performed by scanning for the target pattern. Scanning for patterns can be viewed as classification with large shared parameter networks. Scanning an input with a network and combining the outcomes is equivalent to scanning with individual neurons. The first level neurons scan the input. The higher level neurons scan the maps formed by the lower level neurons. And a final decision layer, which could be a MAX or a perceptron or an NLP, makes the final decision. The scanned block can be distributed over multiple layers for efficiency. At each layer, a scan by a neuron may optionally be followed by a pooling operation to account for deformation. For two-dimensional or higher dimensional scans, the structure is called a convolutional neural network or a ConNet. For one-dimensional scans across time, it's called a time delay neural network. We have thus far arrived at the CNN model through the perspective of scanning an input to obtain shift invariant detection of patterns. In the next couple of lectures, we'll arrive at the same model through a more historical biological explanation, see how we train it, and then see some extensions.